So hello, everyone. Welcome to another seminar of the Spring 2022 BERD series. So before Michael starts his discussion, I want to remind everyone that the webinar will be recorded automatically and all participants are muted during the webinar. So please use the Q&A box. If you have any questions, I will help the speaker monitor the questions. And we will also share the slides with you after the seminar. So today we have Dr. Michael Hunter from Penn State Department of Human Development and Family Studies. His work is primarily on developing mathematical models for human development studies. Today he will talk to us about modeling child development with local item response theory. So thank you, Michael, for agreeing to talk to us about this. Take it away.
Great, thanks. As our moderator and I were talking about earlier before we got started here, let's see, I'm relatively new to Penn State. I got here in January. Let's see, I held previous positions at Georgia Institute of Technology and the University of Oklahoma Health Sciences Center. And the work that I did at the Health Science Center is a lot of what we're talking about today. So one project that's sort of coming to fruition slowly and eventually from that position that I held there. I wanted to give a little bit more overview of the kinds of work that I do as well. So that's sort of in this next bit here. So in general, kind of an introduction to myself, I try and tackle kind of three broad areas: software, dynamical systems, and applications. The software development is basically building tools to do the kind of methods that don't exist yet, and kind of building the tools that let those things happen. The dynamical systems is really the core of what I do. It's sort of modeling change and development over time. A lot of what that does is around differential equation kinds of models. I think those are the kind of key bit there. We'll talk about something a little different today. And then there's sort of a set of applications. Today, it's really about kind of these two that I would highlight. So it's this kind of unknown dynamics. There's some kind of unknown change process that's going on in child development. And we're going to use kernel smoothing to figure that out. And that's sort of the core of what we're doing here today. A bit of an outline of where we're headed. So it's really the application is focused on the Ages and Stages questionnaire, which is a particular child development questionnaire used on children from age about 2 months up to about 5 years. And the particular structure of this scale, there are a lot of aspects that are really good about it, and there are some aspects that make it really difficult to model change over time. So it's really good at a single time point for assessing where a child is at in those kind of ages and stages. But it's not really built to assess how children change over time at the within person level. So we'll talk about how to link scales and review a little bit of material on that. That's where the kind of new methods development is all at. It's this new method of linking scales within the Ages and Stages questionnaire. We do some simulations to make sure that this method sort of even works a little bit. And then we apply it to real data that comes from the Oklahoma project that I was working on. So it'll be a large data set on a child home visiting program where we're trying to assess at-risk children. So very young children, usually born in kind of poor or impoverished environments, to younger mothers, and interventions. And we want to assess the interventions on these children to see how they're doing. If we have time, we may or may not. Or if there are questions, the kind of unknown question at the end is, what else are you working on? I've got a couple things kind of hidden in the secret slides for other stuff that we can talk about. So without kind of getting into too much detail on that, this is sort of where we're headed. The first item, again, is that Ages and Stages questionnaire. So a lot of information on the slide, kind of small, too small to read, but it's generally showing the outline of the Ages and Stages questionnaire. It's built into 5 different subscales. Communication, gross motor control, fine motor control, problem solving, and personal social skills. And there's sort of a set of items in this scale that addresses each one of these. And there's kind of different versions of those items for every kind of age grouping. So across the kind of different columns of this table, you've got the different scales. Across the rows, you've got different age categories. So it goes from 2 months, 4 months, 6 months, 8 months, 10 months, and it goes on like that up until 60 months or 5 years. So there's a lot of different items, a lot of different things that you can do in here. kind of the details of the table are not super important, just sort of the big picture that we want to see. As I kind of alluded to before, there are a lot of really good qualities about this ages and stages questionnaire. It has good face validity, content validity. The items really hang together. Retest reliability is really good. If you have different clinicians rate the same child, those tend to agree. Correlates really well with other kind of gold standard scales. So it has good construct validity, good concurrent validity. It seems to predict other kinds of things, kind of longer term outcomes and things like that in an unbiased way. The predictability is a bit of a question there, but these are sort of good things that you'd want for a one-time assessment of where a child is at developmentally. There are question marks really mostly about how to apply this as to measure a trait that changes over time. So again, you have that face validity, content validity, so it sort of seems appropriate at every age, but a lot of these things haven't been investigated, and it's really due to the structure of the measure over time. It was designed as a clinical measurement tool for single point in time assessment. Essentially, the score that you get out, kind of the response to each item is basically the kid's doing fine, we're a little bit concerned, or the kid is delayed on whatever one of these constructs it is. You basically get three things out, and the aspect that needs to be tracked over time is, well, is the kid doing fine for a 2-month-old? Is the kid doing fine for a 6-month-old? Is the kid doing fine for a 5-year-old? What's doing fine at each of those ages is a different sort of thing. In terms of, think of like the communication abilities of a 2-month-old. Usually it's like kind of example items are things like, does the child make eye contact? Does the child smile in response to things? Whereas for a 5-year-old, you expect much higher level of communication.
Michael, can I ask a quick verification question?
Oh, please.
So
yeah.
can it be possible that a kid doing fine in 1-year-old, but in 5-year-old, not so much, so that
Absolutely.
Switch? Okay.
Yeah, this is the kind of thing that we'd like to track exactly. So if you give this assessment to one child at 2 months old and again at 5 months old, you want to be able to track not only were they doing fine before and not now, but how much have they changed? Have they sort of kept pace on a single dimension? Have they kind of kept pace with other children of their age? Are they leading development? Are they kind of lagging developmentally? We want kind of even more fine-grained quantitative information out of that. That's a good question. Thank you. Let's see. Any other questions before we start to move on from the ages and stages questionnaire? Okay. Let's see. So again, I talked about this a little bit before. So it's the ages and stages questionnaire is really used as a first level screen. It's relatively quick to administer, which is one of the reasons why it was included in the study that we're eventually going to be talking about. And one of the goals that we wanted to do on this project was to be able to monitor child progress. So it's really just saying that we want to keep track of the child over time and see how they're changing, if they're keeping pace or lagging behind. So this is 5 panel plots. On each plot, the horizontal axis is the version in months. So it's from 2 months up to 60 months. And then each of the panels is one of the different subscales. So the gross motor, communication, fine motor, and so on for each of these. They've got raw data plots pointed on here, and I've got kind of smooth group means for a set of different home visiting programs, a set of different interventions. And the key thing that I want you to look at is, look at these group means and how they change over time for communication. They sort of go down at this 20-month period, and then sort of go up a little bit, and they sort of wobble around. But overall, they're relatively flat and sometimes go down, which is not what you'd expect out of any reasonable measure of child development. These are not kids who are these 60-month kids who have a mean around 50 or something like that, have developed, and they're just typical for their age. They're not really of the same developmental level and showing the same capabilities as a 2-month-old. they've progressed, they're just not progressing relative to their age group, which is how this measure is set up. It's set up to be a standard compared to your age group. And what we want is to have everything on the same scale, where a 2-month-old score is sort of meaningful in relation to a 5-month-old score, that you'd expect the 5-month-old to show a lot better communication than the 2-month-old.
Okay, sorry, I have a few questions.
Please.
The lines that you have are the average scores for all the kids, right?
For all the kids within each of those programs.
Yeah, and then you also seems to have the individual lines in the background, sort of.
Yeah.
But you mentioned about an intervention points.
Yeah.
Are those depicted in the figures, or?
So the intervention here is going on all the time for all the kids.
Oh, I see. Okay.
All of these kids are in some kind of intervention program. They're selected, and we have data on them because they're in an intervention program.
But the average curves are based on interventions, or are they're based on all the students irrespective of their intervention?
The different lines are for different kinds of interventions. So this.
Oh, I see. Okay.
This one here is GPAV, which is Give Parents a Voice. This one is HFA. This is I forget the name of that. PAT is Parents as Teachers, and so on. They're different kind of name brand intervention programs.
All right. Thank you, Mike.
So again, this section here where the scores go down, that is not consistent with any reasonable model of child development. We would never expect overall the 20-month-olds to be doing, to have lower communication scores or lower social scores or lower motor scores from 2-month-olds. And that's what we're seeing in the data. So what we'd like to do, what we want to do is develop a method for scoring the ages and stages questionnaire that puts everyone on the same metric, such that you see in general in the group level increases in these scores over time, because they're getting better. You know, the kind of rising tide of development means that everyone is getting better at all these things on average. Individuals within that group can regress and do worse, but the group on average should be going up. Let's see, I think we've talked about that. So the question really is, how can we link these versions of the ages and stages questionnaire? And this gets us to the kind of conventional way of linking different kinds of scales. So because of the way that the ages and stages questionnaire is written, the different items that you get are basically delayed, doing fine, doing fine, somewhat concerned, and then delayed. It's sort of like stoplight, green, yellow, red sort of version. So this is an example item from the 2-month scale. This is item 6. After you are out of sight, does your baby smile when he sees you? So you kind of go away and you come back, does the baby smile? That's sort of the developmentally appropriate version of communication for a 2-month-old. At 4 months old, they give the same item, but you would expect everyone's scores to be higher for the 4-month-olds on average. So basically that whole kind of distribution has been shifted up, but you have the same sort of cut points on it. So when you have items that overlap, it's easy to kind of link these things together and to model that kind of change over age. This is sort of an example of the kind of data that you might have if you designed a questionnaire like this. So you'd have these different versions, 2-month-old, 4-month-old, 6-month-old, 8-month-old, and then you've got all these different items. And every child here, which is in a different row, is given all of the items at every single age. So this first child might be 2 months old, but they get all the items. They get 2-month-old items, they get 4-month-old, and on and on and on up. Now you'd expect them to not succeed, so to speak, at the older items. And you'd expect someone who's older to kind of easily pass the younger items. Now, the kind of statistician might say it'd be great to design your study in this way because it's kind of trivially easy to link the scales in a situation like this. Everyone gets all of the same items every single time. You can score them all together, no problem, easy peasy. The conventional way of doing this sort of in a more limited data way is to basically chain link these items together so that the 2-month-olds don't get all of the items, but say the 4-month-olds get some of the 2-month-old items and all the 4 months. And then the 6-month-olds get some of the 4 months and all of the 6 months, and you kind of link these things together. And for any of the sports fans in here, you can do the same thing in assessing kind of the ability of different baseball players. So if you want to compare, was Don Mattingly a better baseball player than Mickey Mantle or from Reggie Jackson, then you can use the overlap in their careers to make the same kind of assessment and link those different baseball players together, because when their careers overlap, you can use the fact that they're seeing the same pitchers, they're playing against the same players to try and link those scales together. You have to control for age because a baseball player at the end of their career is not playing as well as they did at the beginning and things like that, but you can link these things together. So that's sort of the nice, easy, conventional way of linking scales. What we're talking about with the ages and stages in questionnaire is something a little bit different. The design in this questionnaire is more like this, where there's actually no item overlap between any of the versions. The 2-month-olds only get the 2-month items, the 4-month-olds only get the 4-month items, and so on and so on. So there's actually, instead of having that kind of overlap that we want, we actually have no overlap at all. So if someone knocks on your door and says, hey, I've got tons of data, I've got 6 different versions of my scale, and none of the items are shared in common across different versions, please help me with my data analysis. If you're kind of in a statistical consulting context, you tell them to invent a time machine, redesign your questionnaire, and come back to me when you've designed your questionnaire correctly. That wasn't really an option with the data that we had. This is sort of the real world where we don't have the time machine, and the data are what they are. And this is how the ages and stages questionnaire was designed. So what do we do with it? And so the gauntlet is sort of thrown down, and we say, well, I think we could probably do something with it in this case. And that's sort of the main impetus for, I think this is something we can do with this kind of structure. So again, that convention is you've got sort of, this is sort of a structural equation modeling diagram. I'm not sure how familiar people are with this sort of thing, but say you've got a factor. This is say at age 2 months. This is a factor at say age 4 months. You'd want to use the overlapping items. Let's say item 5 and 6 was the same item. You can see the indexes here are the same. So if those are really the same item, then they sort of are the same thing. And you sort of use that linking across scales to map the factor and kind of keep it constant over age. The situation we have here is a little different. I've got these different item versions. What I'm going to do though is model the change in this latent variable as a function of age. I'm going to say, okay, none of these items overlap, but there's one thing that produces that is say child communication ability, whether it's at 2 months or 4 months or 8 months or whatever months you want. And what changes over age, that's the thing that's causing the change over age, is some kind of developmental trajectory of just child development over time. As kids age, they get better communication abilities. The way we do this, that you can do this, is one version of it is called what's called local structural equation modeling. There are a lot of equations in here, but here's one of them. The general idea is if you have some measured variable, then what you do is you fit a separate model to each of many, many groups, but you use kind of this weighted combination of the rows, this kind of weighted likelihood. And what it does is it lets these, by selecting the weights kind of differently as a function of those covariates, it lets you have the free parameters of the model change in a smooth way as a function of this covariate without having to say what the change process is. So the paper on this is by Andrea Hildebrandt. Here you've got factor loadings related to mental speed. And here it's a function of age in years, 20 years up to 80 years. And what you see is these different items vary in a smooth way over age. Essentially, you're getting at trying to assess how these items function differently over age. And it lets these things change in a smooth way. The panel on the left here is what are called the kernel weights of a kernel smoother. And then the output is these parameter estimates that you get for each kind of window that you're moving along. So that is the basic technique we're going to end up using, is we're going to use this sort of local model estimation with these kernel weights. There are a couple modifications. The first one is easy, is you change from doing a structural equation model, so you have these sort of factors, into an item response model, so item response theory. I'm not going to go into like the big details of what an item response theory model is here. If we have questions about that, I'm happy to address those. But the kind of too long didn't read version of item response modeling is it's a lot like factor models. It's a lot like structural equation models, but it's tailor-made for ordered categorical responses. If you have kind of 0, 1, 2 as your responses to a set of items, and you want to be able to account for the kind of difference between a 0 and a 1 being different from the difference between a 1 and a 2. So these sort of kind of different categorical data, and it's not continuous, then you'd use an item response model. That's a classic way of doing this. So that change is just switching out one kind of likelihood function for another. There's nothing too crazy going on there. The second extension here is really trying to do this when you only want some of the parameters to change smoothly and you want to fix the rest of them to be the same. So in the example that I showed before of the local structural equation model, all of the parameters were allowed to change as a function of age. Here, I don't want all the parameters to change as a function of age. I can't actually do that. The model doesn't work if you try and do that. All I want to do is have one parameter change as a function of age. I just want that factor mean, that one factor mean to change as a function of age. And I want to say everything else is the same across age. The mechanics of how you do that make some of the model fitting a little bit more difficult. So in the local structural equation modeling version, essentially you could just do this in a kind of silly, kind of easy way. All you had to do was get a set of sample weights, fit a model, put the results in aside, get a new set of sample weights, fit the model, put those results aside, and just keep doing that and keep stacking up the results. And then that result will give you this smooth change over time. Here, I've got to fit all of those same models together as one model. So this is what I would call a massively multi-group model. The version that we ended up running has around, I think it's 126 groups, something like that. So it's a 126 group model where all of the parameters across groups are constrained to be equal, except the factor mean, except that one parameter that's allowed to vary over time. So the idea of how this should work, of how this should solve the problem of linking these scales, it's useful to think about kind of the group mean for a couple of selected groups. So imagine the group mean on the communication scale of the ages and stages questionnaire for kids that are exactly 2 months old. So, okay, it looks like this. Here's the distribution. Here's where we think they all are. Then imagine the same group mean, the same population, but instead of 2 months and 0 weeks old, they're 2 months and 1 week old. You've got a set of people that are just 1 week older. And then, just 1 week older than that, and just 1 week older than that. And it just slowly accumulates this tiny change. That essentially, we'd expect the change between exactly 2 months and 2 months and a week to be smooth and small. At the group level, if we had a large sample in each of those groups, we'd expect that change to be small and smooth. All the way, and essentially by kind of linking those small groups up together, you could accumulate change all the way from 2 months up to 5 years, just by thinking about chaining those tiny little steps together.
Are those groups equally spaced, or it doesn't really matter?
Let's see. And kids come in whatever age they actually are.
Okay.
We have their birth date, so we know exactly
Okay.
how old they are.
So the groups are selected based on the data that you already have.
What we end up doing is, so this is the way to think about it. We don't actually have a large sample of groups at every single age, but we imagine that this is a theoretical idea that they do exist, and that if they existed, you'd have this smooth change.
Mm-hmm.
So again, we expect kind of, if we ignore the distribution aspect, we think there's this kind of smooth change going on here. And I have a kind of visualization that hopefully will help get at something like this, which relates back to the simulation study that we end up running. So here we've got age in months. So going from 2 months up to 5 years, you got some kind of latent ability score here. And what should do is essentially I've got a sample at every time point, and the sample is very erratic. The sample can go, any individual sample member could go up or down at any given time, but the group mean sort of changes smoothly. So I've got the group mean sort of traced out as the solid line. I've got sort of 68% or 95% confidence intervals saying, okay, here's where kind of most people lie at any given time point there. So again, we're not saying that the individuals change in a smooth way between measurements. We're just saying that the group changes in a smooth way. The kind of ensemble mean shifts in a smooth way over time. So we wanted to try this out, and the safe way to try this out is with simulation data. So we generated data according to a couple of different conditions, really trying to answer these questions. So first, you try the easiest one first. What happens when you actually have continuous data instead of ordered categorical data? Then you want to see, okay, now if I change it to ordered categorical data, does that work? Can you estimate the mean? And the variance, actually, how much the scores change over time, because there are some developmental theories that might suggest that children kind of diverge, kind of increase in variance or decrease in variance at different times. How do you do inference? What happens if the changes aren't smooth? What happens if you just throw independent scales together? Do you end up linking these independent scales? The kind of summary of all this sort of stuff is continuous items work. The ordered categorical data works. You can estimate both the mean and the variance. You do inference with bootstrapping. And I've got some simulations that investigate non-smooth changes in independent scales, but those are sort of secret slides at the end that we can ask about. To dive a little bit more detail into this, so here's the continuous data case. So you generate data, you've got a one-factor model. There really is one trait. It changes, the factor mean changes over time. I had a colleague of mine actually generate the age varying factor mean. I don't know how the colleague did it. You just, here's the mean at each age, and that's what I used. So I don't know what structure it really takes. The full data is that kind of version where you have every person getting every single item. What I call the missing data is when everyone only gets the age appropriate item. So it's those blocks. There's no linking between them. This was with, the simulation was with 1,000 people and only 3 different versions. So you only have these kind of 2 cut points where it changes from one version, then there's a cut, and then there's a second version and a cut and a third version. And let's see, 9 items total with 3 items on each version. Nice, small, contained example. Again, here's that full data where you've got everyone getting all the different versions. Here's what I call the missing data case, where you really, this is the kind of experimental condition, like everything better work with the full version. Like that's the sanity check. Everything should work with that without any problems. And then you hope that the missing data condition works similarly. So this is what comes out. So let's see, in the left panel, we've got the estimate for the mean. In the right panel, we have the estimate of the variance. The green line here is the true factor mean as a function of age. The black and the red lines are the full and the missing data cases. And you see that they basically track both the green and the red lines, both the full data and the missing data track basically very similarly to each other. And both of those track very closely to the true data pattern. It's not as good, nowhere near as good for the factor variance, but I think factor variances are just harder to estimate. And where there are kind of big deviations between the true data and the recovered estimates, they sort of look the same for the full data and the missing data. So I'm not super concerned about those. I think it's sort of a data thing that it's just harder to estimate the variance than it is a mean. And that the particular data that I generated were kind of showing this pattern that indicated that the variance should go a little bit crazy in certain places. So this was pretty encouraging to me that it seems to work. The method that we're developing seems to work. And this is surprising in the sense that there's no item overlap. Again, there's nothing in common between these scales that we're generating. So in theory, it should be kind of a difficult problem. And this method seems to work pretty well. As far as the other parameters in the model, we estimated kind of full factor models on those, and everything seemed to work similarly the same. So then we're going to step this up and try it on the real data. So the subset of the data I'm pulling out for analysis is one of these intervention programs called Giving Parents a Voice. It's funded through an Oklahoma Child Home Visiting Initiative. It's called MECHIV. They were annually surveyed, rolling recruitment from WIC and Medicaid registries. Let's see, if the mother had more than one child, they sort of always filled it out on an index child, the oldest child. The demographic things are essentially what you'd expect. Mostly female caregivers, younger age, lower income. These are Oklahoma data, so a lot of them are from Tulsa and Oklahoma City. That's where the population centers are. Relatively small household size, kind of race and ethnicity makeups, and all these other things that kind of match the lower income folks in Oklahoma that we were targeting. Child gender, obviously much less skewed than parent gender. Let's see, these are the different sample sizes kind of for each version of the ages and stages questionnaire. Relatively uniform starts dropping off at the upper end there for the 5-year-olds, the 4 and 5-year-olds. A lot of that is due to, the interventions are targeted at young children. So, we would expect to see that, but pretty good coverage across the whole range of the scale. So again, to refresh your memory on the problem we're trying to solve. So we've got this, these different subscales of the ages and stages questionnaire. We have these kind of group means that seem to suggest that 18-month-olds don't communicate as well as 2-month-olds, which we're pretty sure is wrong. And then the solution when we apply this method is we get data that looks like this instead. So in general, you see a much more clear upward trajectory. You don't see this dip at 20 months. Everything seems to be kind of showing that in this sort of scale of the latent dimension that we're creating, all the 5-year-olds are communicating much better than basically any of the 2-month-olds, which is what I would expect. And that pattern sort of repeats for gross motor ability, fine motor ability, problem solving, and personal and social ability. So basically for all those scales, you get this kind of separation where there are virtually no 5-year-olds that communicate that, are developmentally at the same level as a 2-month-old. So this seems to suggest that, again, this is what we're hoping for and what we're looking for. And then you kind of have everything sort of on this common metric where you can start to ask questions about comparing these different home visiting models. You can ask questions about, giving parents a voice as compared to parents as teachers and seeing if there are differences in those intervention programs. Now, one of the things that we did, so I call these, here the label here is a factor score proxy. So we actually did, in making these, was we wanted to make this as kind of user friendly as possible. So, I'm fitting this as like a 127 group item response model. It takes, 20, 30 minutes to run. I don't expect people in the field to be doing that kind of scoring, when they're scoring the ages and stages questionnaire. So what we'd like to do is be able to hand folks a tool where, oh, if you just, add up the scores in this way, maybe like a weighted combination, could you produce something that's pretty close to the results of that kind of more sophisticated model? So this is what the factor score proxy is. Essentially, you take the raw score, this is across all the different versions, and you correlate it, make a regression plot with the factor score. So you've got the raw sum score for each of these different versions and each of these different panels, and it's plotted against the factor score that you get for each of those people. And the correlations, range. I think the lowest one might be like 0.8. I think the lowest one is this 0.83 for 4-month-olds, and the highest one is 0.99. There are a few that are like 0.99, where they basically map linearly onto each other really, really well. So essentially what you can do with this is say, okay, if you've got a raw score of, let's say 40 on the 20-month version, well, that should map to, a factor score of about 1. And you can just tell them, multiply your raw score by this number that depends on the version, add this other number to it for an intercept depending on the version, and then you can map and you can get these scores that are on the same scale, no matter what version that you got. And one thing you notice, so I can use the same scale on all these, essentially the big thing that happens when you go from 2-month-old up to 60-month-old, there's a little bit of a change to the slope, but there's a big change to the intercept. Essentially what's happening is you just adjust the scores up by an intercept factor. You just sort of add a constant to the scores to adjust the scores from the 2-month-old up to 5-year-old. So this is sort of the mapping between those raw scores into the factor score proxies in a way that makes it easier for folks to use. When we look at, so these are, I didn't really talk much about the thresholds in here. The thresholds are the things that, the dividing lines, the cut points between delayed and somewhat, very delayed, like very concerned, somewhat concerned, and doing fine. So those cut points between those were things that we're estimating from the model. And this kernel is the model that we're using, that we're proposing. Without the kernel is the ones that we're not doing. And the item here, generally we'd expect that the items basically have a higher threshold as the items increase, because the later items are just have them sorted, so that the earlier items are for the 2-month-olds and the later items are for the 5-month-olds. So essentially those thresholds should move kind of up over age. And we see that when you have the kernel method applied here, the thresholds sort of trend upward for the first category and for the second category. But if you don't apply this kernel, basically they stay flat and nothing happens with them. They're saying that the same difficulty of the items occurs for later items and for earlier items. A similar thing sort of happens. Actually, the similar thing doesn't really happen for the factor loadings. So in the item response theory terminology, this would be like item discriminations. Essentially, the factor loading, when you use this kernel method or not, that's on the horizontal or the vertical axis here, the factor loadings stay about the same. So this line that I have here is an identity line, slope of 1. Essentially, the items function in the same way. They sort of discriminate, they have the same kind of characteristics in relating to, they sort of relate the latent factor to the items in the same way. They sort of have the same slope, but a different intercept, again, basically. Those thresholds kind of give an intercept, and the factor loadings sort of give a slope, and the slopes are basically the same. Whether you use this kernel method or not, it really only kind of forces items into an order on a scale without changing sort of how the items function. When you look at the group means, again, comparing these two, here I've got a red line indicating that the recovered factor mean over time. Then I've got individual factor scores, either using the kernel method or not using the kernel method. And when you don't use the kernel method, again, you see this flat line, abilities kind of stay about the same regardless of age. And when you use the kernel method, everything sort of goes up how you'd expect. And even the shape of it is basically what I would expect, where you have kind of rapid growth at first and it sort of tapers off later on. So I know I'm getting short on time. I want to wrap this up. We've got about 15 minutes here. So some couple ideas of conclusion here. So one is kind of aspect is on specific things that you can conclude about the ages and stage questionnaire, and the other thing is stuff we might want to conclude about the method. So one, we seem to be able to, with this method, use the ages and stages questionnaire to model change over time, to actually model development. Not just as a screener, not just as a one-time assessment, but potentially to use this multiple times to track change over time, to do progress monitoring. So this seems very promising. Second thing, I was really surprised when I was actually running this, that these sort of linear proxies where you just take, a multiplicative factor and an additive shift to the raw scores, that actually gets you really, really close to the factor scores. That the correlations, 0.9 and up for a lot of those subversions seems, it's not the ideal way to do it, but for a field study, it's something that you could put out in a manual for how to adjust scores to do progress monitoring. Very doable, pretty easy to manage. And some of those proxies are currently being used in the field now. Again, about the individuals versus groups. So the model is assuming that the group mean moves smoothly. So again, think of that video where I have the kind of ensemble mean, you got these data kind of all flying around in crazy ways, but the group mean kind of moves smoothly and kind of trends upward, even though the individual means, kind of the individual scores could be declining or inclining or kind of doing anything you want. And then you can think about using this sort of scale linking as a preliminary step to doing later dynamic modeling. As far as the method is concerned, again, I'm sort of like suspiciously pleased with how well it works. Anytime something works, I sort of start to think, that might work a little bit too well. So I'm a little concerned, frankly, a lot of the time. But if you assume that the latent mean is a smooth function of some covariate, then you can actually link those scales without common items. That's what I'm finding here. Now that's kind of a big if in some settings outside of like child development. I'm not sure what covariate that might be that could kind of link for in other contexts, scales like this. But even if it only works, even if the primary application is in development, I think there are enough factors impacted by development that you could use age as that proxy in a lot of settings. The simulation seems to work at recovering those parameters. I didn't talk about it, but the method seems to fail gracefully. So when there are sort of no reason to link scales together, it doesn't give you a result that implies they are linked. Let's see. Then some future work on here would be investigating things about actual tests of measurement invariance for this sort of thing, to see if the items see if you can pick up when items aren't functioning the same at different ages. Or looking into different methods for inference on this. So right now it's using some bootstrapping for inference, but there could be something better out there. Just to wrap up, I want to thank folks for coming and listening to me talk about this stuff. I want to also thank Chapin Hall and the Pew Charitable Trust for giving some funding to do something crazy like this. Now I think we have a little bit of time for questions now.
So while people might be thinking about questions, I actually have a question just because of my lack of background in the science of this problem, right? So you are trying to develop a tool that monitors the progress of kids. Mm-hmm. So what I wanted to say is how because you said that the row scores, the proxies that you guys are creating for the factor scores, they are helpful in the field.
Yeah.
I just wanted to get an idea of how the system works. So you all already have to have data to get the factor scores, and based on the factor scores is how you decide what the weight should go into the row scores. So did I miss something there?
Yeah, I think I probably just didn't explain it very well. So we collected all this data. Mm-hmm. The data collection is ongoing, but we analyze the data that we have. We can develop these factor scores and the factor score proxies with the data that we have.
Oh, okay.
Now that with what we have, I can say, okay, I can create a manual that says, okay, if you're out in the field and you're doing the ages and stages questionnaire, you're using the 6-month version, you have a raw score of 40. Okay, multiply that by 2 and add 7. Mm-hmm. And that'll give you their developmental score on the same scale. And then you could compare that developmental score to what they got last time out in the field right there.
I see.
Computations that you could do on your phone calculator kind of thing, as opposed to stuff that you'd need me to run. So then they can say, okay, last time you had a developmental score, last year you had a developmental score of minus 1.5, and now it's plus 0.5, so you changed by this much, and we think you're doing great, and isn't that so wonderful?
Got it. Okay. So there are 2 questions for you, Michael.
Oh yeah, let's see if I can pull these up. Recording. Okay, the first one is about the recording. I assume it exists, it's out there. There's no reason to expect. So this is a question about linking different versions. I can jump to some of the slides on that. So this was a case, one of the simulation conditions that we did for, I just generated 3 different scales that happened to change. Like if you gave someone a child development scale and a question that comes from their taxes and something else about how many years of education they have or something, you just give them totally different things. What happens there? So the true scores are again these green lines, where it shows this sort of pattern. The black line is the full data case, so you get something that's just flat, and the red line is the missing data case. And in that case, you get something again that's sort of just flat. It's shifted up, which is a little bit odd, but it doesn't show, oh, look, there's this like big change in what's going on. So if you fit this as like separate factor models, if you fit this as kind of separate models and as the linked model, and you get totally different results, that would suggest, that the linking really is not appropriate there. You're measuring something totally different across age. See, there are a couple more, I think, coming in.
And there's one more question for you.
Integrated data analysis. It tries to bring. So the question is about integrative data analysis and using this when you've got data from multiple studies. So with integrative data analysis, a big challenge is sort of harmonizing scales. So you've got, say you've got the Beck depression inventory measuring depression, and you've got the CESD that also is measuring depression, and you want to say like, well, the CESD and the Beck depression inventory, so both measure depression, but they've got totally different items. Mm-hmm. And you want to see if you can sort of link those together. And sometimes what people will do is they'll say like, well, this item in this inventory is sort of like this item on this inventory, so we're going to call those the same item and do something like that to try and create that kind of item overlap. Now, I'm not sure, I haven't really thought about how it could be used for integrative data analysis. Certainly if there's like a developmental or an age component, maybe let's say it's not developmental, let's say it's lifespan developmental age. So you have things like people age 20 up to age 90 or something like that. And you expect, there's a well-known sort of trajectory of cognitive ability, for general and fluid intelligence across that age span. So you could use it in a context like that. The key is you need some sort of like covariate where you would expect kind of, if you were combining two studies and one was say age 20 up to age 40, and a different study was age 41 up to age 60, then you expect the kind of gap between the 40 and the 41 to be very small, and sort of you want to kind of smooth over that gap. I think you could use it in an integrative data analysis context like that, where you're sort of linking up different studies where you've got them sort of very close in age, even if there's no overlap. You could also do it if there is overlap, and it might help in that context as well. So it shouldn't hurt if there is actual overlap in the age there. It should only help make things a little bit easier to link. But the key is you need some sort of covariate. I'm thinking in terms of age a lot, just for the kind of work that I do, but you need some kind of covariate where you're kind of mapping as a function of that covariate. So you need some kind of separate measure that you're linking sort of across. It could be, it doesn't have to be age, it's just the one that I'm thinking of a lot.
Can it be more than one covariate, just related?
Oh, okay. In theory, it should work for more than one covariate. Then you have sort of, you need sort of a two-dimensional kernel smoother, basically. So it gets computationally a little bit hairier, because then you get kind of you have to do it on the grid of those two dimensions. But all the math should work. It just, you might need to run it on a supercomputer or a big desktop instead of on my laptop. These models will run on my laptop, which is great. Okay.
There's one more question to you about the simulation study.
Yeah. So they're comparing the simulation study sample size of N of 1,000 to the actual study. The N was smaller. I think the N was pretty similar. Let me pull that up. And so we have, this is around 100, let's say 125 in every single one of these bins. So you're added up all those bins and your sample size is pretty close. Mm-hmm. And here I list the N of about 1,600. So it's not totally different. We had, so in the simulation study with N of 1,000 spread into three groups, you have 333 and a third folks per group. So that's a bit less, the 333 versus 125 in each group. But not, those aren't, an order of magnitude different from one another by any means. I think you may have been thinking about, the kind of 125 in each group versus 1,000 in each group.
Yeah.
It wasn't 1,000 in each group. It was only 300 or so. So it's relatively similar in size, not, exact, but I think it's close.
I have one last question, Michael. So once you collected the data, once you have the factor scores, so you have these proxies, but did you ever updated your scores with the new data that they might be collecting? And did you see any changes?
I haven't done a reanalysis to kind of update to see what those would be like. It's possible that they would change, but sort of large group means I would imagine stay pretty stable. I'd hope. It's always possible that they could change. They're not by any means, ironclad. And it would probably take about 20, 30 minutes of like computer running time to just assimilate new data and rerun the same models, refit everything, create new linear mappings between them, and just output those. It'd be pretty easy to automate that sort of thing to do continuously. It'd be aggravating for someone in the field to change those things. So I'd want them to be relatively stable and change those things rarely, sort of the same way you update age norms for things.
You could always develop an app. Yeah.
And if I was doing the app, I think, I could actually have it do the factor scoring the full way. If I'm going the app development route, why not go for broke?
All right. It's already 5, I think. Okay, thank you very much for the interesting talk.
Thanks for all the questions. It's been fun.
Yeah, thank you. Thank you everyone for joining us. So have a nice day. Bye.
Bye-bye.